Next we have Douglas Gransberg. He's going to present on recognizing life cycle cost sensitivity for pavement preservation treatments. Douglas Gransberg is a professor of construction engineering at Iowa State University. He received both the BS and MS degrees in civil engineering from Oregon State University with his PhD in civil engineering from University of Colorado at Boulder. He was a faculty member at the University of Oklahoma and Texas Tech University before joining ISU. His research spans the full life cycle of highway engineering, construction, and maintenance, from the procurement of new projects using alternative project delivery methods such as construction manager, general contractor, and design build to the preservation and maintenance of pavements and bridges. His research has received awards from the Transportation Research Board, several U.S. state departments of transportation, and the New Zealand Transit Agency. Let's please welcome Mr. Gransberg.
Thank you very much. Well, thank you very much on this. This is a topic that's near and dear to my heart. I came to academia late in life after being a public engineer, to include a director of public works for about 20 years. And so as a result, I was bringing in the baggage that money does matter. And as my wife calls me, she says, I'm terminally pragmatic. I don't have an idealistic bone in my body. And this topic right here is one of those things where there's going to be a lot of people, I would assume, that are going to not like what I have to say. But has anybody ever heard of the old fable about the emperor has no clothes? I'm here to tell you, the emperor has no clothes, okay? I'm not against life cycle cost analysis. I'm all for the philosophy behind it. But unfortunately, as engineers, we teach you in the university that it's okay to make assumptions. You know, it's like, what was it, Archimedes said, maybe he wasn't the right one, if I could have a lever long enough and a place to stand, I can move the earth. There's the two assumptions, okay? So, with that being said, let's talk about life cycle cost analysis. And I got to tell you, I didn't get my PhD until I was already an associate professor. I did my doctoral dissertation on life cycle cost analysis on basically the holy grail, asphalt versus concrete, the old white guys versus the black guys. And that's where I started discovering that what we were taught in our undergraduate engineering economics classes might not be applicable to things that have long lives. You got to remember, engineering economics came from industrial engineering. You know, a bulldozer has a salvage value. I don't know that a pavement does. Are we going to ever sell it? Probably not. It probably costs more. So let's talk about what's in here. Is Siva in here from Federal Highways? No, he's kind of I gave him a heart attack. I just finished a NCHRP synthesis on alternative designs, alternative bids, and made the recommendation that we don't use a life cycle cost adjustment factor, based on the fact that 6 states bid concrete against asphalt head up, and 67% of the time concrete wins. So it's a market condition thing. So these are the issues that we've identified in life cycle cost analysis, and I'm going to go through each one of these in detail, and I'm going to give you results of empirical research that's been published to prove that these are things you need to be sensitive to. So first and foremost, present worth analysis. The bottom line is, why do we use net present worth? Well, it's because we come from the low bid mentality of procurement, which is, I want it to be the cheapest it can possibly be today. Now, this is the pavement preservation group. This is a group that understands that if you buy a cheap pavement, you have an opportunity to buy another cheap pavement at a much earlier stage than which you would like to. And so the problem we have here is a computational problem. You have to come up with a way to compare apples to apples. So in theory, the net present value is going to be multiple lives. And so if I have something with a 13-year life and something with a 17-year life, I'm going to probably have to evaluate it over 134 years. Does that make sense? I mean, what's the price of asphalt going to be tomorrow? Yeah, so why does discounting it by 3% a year for the next 30 years make you think you have an accurate number at the end of the day? Realities, okay? We can use, there's an easy way out on this, and that's the equivalent uniform annual cost. You're comparing it on an annual basis as opposed to making an assumptions. It gets away from having to add an assumption for how long is it really going to last, which, by the way, that's a big assumption. And, you know, how are we going to change it when it reaches the end of its life? So, period of analysis. What do you use for your period of analysis? Does it include a rehab? Does it include a replacement? How often do we replace it? You know, these are numbers that greatly change the life cycle cost at the end of the day. And so the bottom line is, as you read up there, you know, I did a research project for Texas on seal coats back in 1996. I don't know if we got any TxDOT folks here. Did a little synthesis on it. And what was interesting is we found that 50% of the roads in Texas that TxDOT is responsible for are unbound pavements with chip seals on them. They're not hot mix or concrete. So half the time the Texas DOT is getting their report card graded by a chip seal. That's why it was an important thing. They had chip seals out there that were 20 years old. 20. We always say 5 to 7 years, right? Well, you know, you get a good subgrade and you get low traffic, and if you get the right environmental conditions like no freeze thaw, which they can get in Texas, you can make these things last longer than that. And so that's just one of the examples. You know, one of the things that a guy named Steve Cross, and I forget what Parsons' first name was. This to me was probably the most believable study on asphalt versus concrete. This is in fact, Scott, I think, lives up there in Salina, Scott Bergkamp. He may have even seen this. But this is one of the interstate highways where it was going through an urban area, and they couldn't get the right-of-way for one direction. I guess it would have been, I forget, yeah, the westbound lane. Sherman, Kansas, I guess. At the time, the policy was that you had to put concrete down for interstate highways that had a traffic volume above so much. And so they had originally designed this particular piece of interstate to be all concrete. Couldn't get the right-of-way, went ahead and built the one direction that they did have the right-of-way for. A year or two later, they got the right-of-way, and the policy had changed to where you didn't have to do it. And so they went ahead and built asphalt. So now you got the perfect comparison. You know, it's the same place, same traffic. Yeah, there's a 2-year age difference, but that's not a huge thing. And what Steve did was to go to KDOT and get every single dollar that had been spent on those sections and just accumulate them. Okay, this isn't a life cycle cost. This is cumulative costs. And you can see where you had the asphalt when it came in. He actually, I think, brought the asphalt forward 2 years. So that maybe that's suspect. But what was interesting was to see the idea that we have that, asphalt costs less, requires more maintenance, doesn't last as long, versus concrete costs more, lasts longer, doesn't require as much maintenance. if you extrapolate those curves, at the end of the day, the asphalt never catches up with the concrete. And it just has to do with the fact that they had a reinforced concrete pavement section, which is not easy to take out. It costs more probably to take it out than it took to put it down, and then had to be replaced. So, you know, just other issues. What discount rate do you use? You know, the Federal Highway Life Cycle Manual talks about using, I believe it's something comes out of OMB now. It used to be the Consumer Price Index. Does anybody know what's in the Consumer Price Index? Shampoo, aspirin, carrots. I mean, the only thing that's in it that relates to what we do in highway construction is gasoline. And the idea is it's a top-down, a global thing. This is the change in the buying power of the dollar. Well, I can remember times where we've had points where, because of oil prices and the availability of asphalt binders, that we've had incredibly high costs for asphalt concrete. And this is just what I got out of my which one of those numbers is right? New Zealand is a real good example. I've been doing funded research for the for NZTA since 2004. They have a life cycle cost mandate for their pavement design system. In New Zealand, you have to have 25,000 ADT to be able to justify putting down anything other than an unbound payment. So if you want to put down 3 inches of hot mix or 6 inches of concrete, you've got to have 20. They only have 3 million people there. So getting to 25,000 ADT is only going to happen in Auckland, Christchurch, Wellington, and that's it. I actually did an invited lecture there, and got in trouble with the Minister of Statistics, or whatever they call them in New Zealand, because I made the comment that by picking an interest rate, you've done your pavement design. You've picked the pavement type. So is that the unlicensed practice of engineering by an economist? It was meant to be a joke. It wasn't taken that way. The bottom line is, this is not something you can blow off. You have to test the sensitivity of the discount rate assumption to what you're actually doing. You know, these are the possible ones. Global, that's the old Consumer Price Index, or whatever the country's using. You can go into an industry-based things. You've seen construction cost indices. If anybody subscribes to the Engineering News Record, they have a really strong, very robust database of commodity pricing and how it's changed over time. And then you can get into econometric databases, which are basically taking the feature of work that you're building and taking it down to its commodities like asphalt, steel, cement. Here's a Monte Carlo simulation that we ran on one of our previous projects using 3 different interest rates, the 3 different types that I have here. One was the national rate done by the Engineering News Record, which is their construction contract or construction cost index. And then Caltrans also does its own industry level interest rates. If you look at the numbers, and I realize it's converting e to the plus 16 might not be the easiest way to determine this, but that bottom line basically says that if we use that first index as our discount factor, asphalt is always the lower expected life cycle cost. If we go over to the next 2, it switches. It goes from asphalt to concrete. And it has nothing to do with the road. It has nothing to do with the design input or the traffic. It's just the interest rate that's assumed. Here's one that one of my master's students did way back when. She was just looking at, this was in Texas. They have basically 4 different ways that if you were a consulting engineer doing a pavement design for a TxDOT district, and this is asphalt pavement, all 4 of these are recognized ways to come up with an adequate design for the same design inputs. What this shows is not how much asphalt's in there. That's the full section, including whatever the base and the sub-base could be. But if you just, the reason I put it in here is if you look at the total thickness, the thickest section is never the lowest life cycle cost. However, based on the discount rate that I use, I can justify anywhere from this one, the second thickest, to the thinnest. And again, that's just a graphical way to show you just how sensitive this is. It's not something that we as engineers should be just saying, well, that's not our problem. That's the economists. They told us. Federal Highway said we have to use 5% or whatever the going rate is. Same thing happens when you start bringing in user costs. You know, user costs are a model of what it costs the traveling public to drive down our roads. No money exchanges hands. So again, we're dealing in theoretical possibilities. If you get into urban freeways, those of you that do pavements, your user costs can actually be 3 and 4 times what the actual construction cost of the road is. And so we handle that by saying, well, we're only going to use 10% of the user costs in making our decisions. So my question is, why did you pick the number 10? Why isn't it something like 11.82? That, you know, that just shows there's something other than just grabbing a number. Again, it's an assumption that's being made. The World Bank actually uses a thing called social discount rate, and those of you that are into asset management, I've been dabbling in this for bridge, coming up with low volume bridge asset management funding decisions. But the idea there is it has to do with what's the impact of the asset to society. Okay, so it includes the eco or socioeconomic factors of a given transportation asset. So why would we discount the user costs using a financial discount rate when there's no money that changes hands? Why wouldn't we use a social discount rate? And so this is just an example of looking at concrete versus asphalt, where you discount the agency costs with the financial rate, whatever it was, and you discount the social cost, the user cost, with a social discount rate, and you'll see, again, it flips. So it's sensitive to what number goes into each of those input values. Got ahead of myself here. You know, the bottom line is we really need to recognize when we're picking an arbitrary number. Most of my recent research has been done in the area of construction finance, specifically coming up with a way to do more construction each year with the same budget. I've found the ripest field to plow is contingencies. You know, why are we tying up money that we may not need? Well, we're being conservative. But what's really interesting is you go around the nation and around the world, and you'll see there are mandated contingency percentages at different levels of design development. And so if it's, you know, at the 30% stage, the agency says they have 25%. That means it's 25% contingency on a chip seal and 25% contingency on a segmental bridge. It's the same amount. It should be risk-based. And so one of my things I try to do is get away from having arbitrary numbers. You know, I don't mind using percentages if that makes sense, but they should be rational. They should match the problem that you're trying to get into it. It's the same thing with arbitrary weighting of user costs. Residual value. This is really starting to get into the abstract. You know, what's the chances that the state of Tennessee is going to sell the interstate over here? I mean, what are the chances of me selling my Honda Pilot? I will sell it at some point in time, or trade it in or give it away. But I don't think we're going to do that with a lot of our public works. And even though I recognize what the theoretical background is for computing a residual value, I'm trying to carry the message is you need to be looking at things like this with malice and forethought. Not just saying, well, we'll use straight line depreciation. I hate to tell you this, nothing depreciates in a straight line. You know, my car, the minute I drive it off the parking lot, it depreciates more than it will in the 5th year of service. It's that simple. But what we've done is we've gotten to that point of give me a long enough lever and a place to stand, and I can move the earth. In other words, I can assume all the computational complexities out of the system and be able to come up with a number that I can compare to another number and pick whichever's lower. Volatility issues. You know, I got resensitized to this on the alternative pavement or alternative pavement bid synthesis we just finished. Bottom line is we make an assumption during design and make a pavement selection, probably based on life cycle cost. How old is that assumption? The one that said, okay, we're going to use concrete because it's got lower life cycle cost. It's at least a year old by the time we get to the point where we're bidding it. Might be 2, 3, 4 years older. If you look at the STIP, those are 5-year plans, so it's probably at least 5 years old. So what was the price of diesel or of gasoline 5 years ago? Heck of a lot higher than it is today, right? I mean, like double, almost double. And that's the issue that we have to be sensitive to. And that's what I'm trying to do here. I'm not trying to assassinate this particular thing. I'm trying to get people to understand that when you make million-dollar decisions in asset management programs, you really ought to think through the assumptions that you have. This is a good example from one of my research projects we did for the Oklahoma Turnpike Authority. We were using an econometric model and a Monte Carlo simulation to estimate the impact of various commodities. In this case, this was actually a bridge rather than a pavement. There was some pavement in there. But you can see that the most sensitive component from a standpoint of volatility, and this surprised me, and that's why I picked this, was Portland cement. It wasn't asphalt over the period in which we were looking at it. You know, the idea is we have these myths. Concrete's always more expensive and it's less volatile. Well, it is until you have a cement shortage, which is exactly what happened in this particular case. Anybody remember the Olympics in Beijing, where steel suddenly, something that had been not that volatile, suddenly became incredibly volatile. So bottom line is, I think in transportation we have very complex systems. And as engineers, we want to be able to solve the problem. In the university, we've been told it's okay to make a bunch of assumptions. Life cycle cost analysis is something that cannot be done without a sensitivity analysis on every single input variable. I don't care if it's a mandated number, okay? You need to be able to sit down and say, okay, if I'd have used 3.5%, I'd be using a different pavement type rather than 3%. That's the key message that I'm trying to get across here, is that we just can't blindly compare numbers. This isn't like opening the bids on bid day. I mean, that's an easy thing to do. Anybody that knows, when we're making these kind of decisions, we're making long-term decisions. And the bottom line is we're not going to have a whole lot more money. How many agencies in here are involved with public-private partnerships now? Yeah, how many of you were doing them 3 years ago? Yeah, I mean, there it is. I mean, it's we're out of money. Private sector's got money. Private sector has a different set of decision criteria for pro forma analysis. The private sector has to be able to make a profit. The public sector just has to break even. And so understanding the things that are in the mandates and exactly what they do to the outcome of the equations and to the decision that are ultimately made is extremely important. Now, we can play around with the deterministic versus stochastic. You know, essentially, deterministic is what you learn. You know, concrete's going to be $150 a cubic yard, you know, delivered to the site. It's one number. We're not looking at what it was before, what it could go to, those kinds of things. In the last 3 years, I have seen an increase in the amount of computing power and the ability to be able to use very simple software tools like Excel to do things that used to require code writers. I had a master's student who actually wrote a neural network. That's machine learning, artificial intelligence in Excel using no external software other than a couple of add-ons that were problem solvers. She couldn't have done that 4 years ago. Excel just wouldn't do it. We used it, we tested it in Montana on estimating construction costs at the very first day that a project is assigned a project identification number. So in other words, you have the least amount of detailed information from which to create the budget, which is the other unfortunate thing about public works. We have to set the budget before we know anything about the project. We improved the estimates by 50%. The chief engineer told me she thought if this tracks, because you're talking about 5 years from now, that she might be able to let 6 projects more a year with the same budget just because she isn't tying up money. Where is the money being tied up? Mandated contingency for every project. I mean, when I was a Corps of Engineer guy, I had my mandated contingencies when I did estimates. Bottom line is, back then, I mean, I went to school when we had slide rules, all right? You know, we didn't have cell phones. We didn't have computers. Well, we did. We had card machines. It was impossible for an average public agency to devote as much time as they needed to exploit the data that they had already in their archive. That's not the case anymore. At Iowa State, we did a project where, with an app on an iPhone, you heard Dave talking about that. Construction inspectors, they do their daily work report on their iPhone. It goes to the cloud. At the end of the day, you have an as-built schedule for the project without talking to the CPM. So if there's been a delay, you want to sort one of those things out. Opened the Panama Canal here in June. They used a similar system to do that. They, by the way, didn't use CPM scheduling. They used linear scheduling, which is a lot more data-driven and a lot less judgmental. Anyway, the whole idea here is we've got the data. Just to show you something, this comes from an ex-PhD student's thesis, Dominic Pittenger. I don't know if anybody's met her. She's a assistant professor at University of Oklahoma now. But if you look at the difference between the deterministic uniform annual cost for a pavement preservation treatment, in this case we're doing it dollars per lane mile, 3 different discount rates. You'll know that when you hit that point, you're now at the 37th percentile, okay? Each one of these gives you a different number. That's the point of this particular table. Cut it down another $700 per mile. Now you have less than a 5% chance of actually having it realize the predicted life cycle cost. Bring it up. Now you're at 82% chance that it's going to do that. This is another one that comes from a regression analysis that she did. You can look at the different regression coefficients. You'll notice that the regression coefficient for the discount rate is the best. Why would that be? I'll play professor here. Because it's between 3 and 5%. It doesn't vary very much. So that's why it's easy to model. If you look at an example where you're making a decision between should we put down a thin hot mix overlay or a 5/8 inch chip seal, using the same one, you can see what the differences are there between low, average, and high. Basically, what she did in this particular one was take a worst possible, best possible, most likely case. In the Monte Carlo simulation, she modeled that as a triangular distribution. I mean, we can all do that. You can see the variations that are available there. Whoop. And you'll notice, if you use the worst possible case, you're going to come up with a very high probability of actually realizing that number. And so, bottom line is, I think we can use the stochastic stuff, number one. What it does is it takes away having to make the assumption that the discount rate is going to be 4%, because that's between 3 and 5. We can model it as a continuous variable between 3 and 5% if we have a mandate. Or we could actually do a little research, go get the data that's available on the internet now, and find out what the inflation rate, if you will, or the escalation rate is for a given commodity like Portland cement or steel or asphalt or aggregate. By bringing that in there, we're minimizing the number of assumptions we have to make. And we're using data-driven analysis, which is easier to justify. With that alternative pavement design and bid thing, the major issue with making that recommendation, which, by the way, I was told I could not put in the report. They didn't believe that I could support it. But the issue is every time you put it in, you have to argue about what the input values are. Well, does your service period include a rehabilitation or not? Why did you 6 states have actually said, throw that out the window. We'll just bid them head to head, and we'll see on the day they open the bids which one is the lowest cost. That, to me, speaks volumes. They don't have to argue with the Asphalt Institute and the Concrete Institute over whether or not their life cycle cost calculations are fairly treating each type of commodity. Life cycle cost isn't as simple as it looks. I mean, that's where I went. Well, on my PhD dissertation, I started out thinking this is going to be easy. I'm going to use the Concrete Institute software to do life cycle costs for concrete pavements, and the Asphalt Institute software to do the asphalt pavements. And I found out that when I put the two things in each one, it tended to be biased, to say the least. I mean, it's the assumptions. I mean, they're not doing something that's malicious. It's just the assumptions that are being made by the people that are writing the software, putting the algorithms up. I think we've oversimplified it, and I honestly believe that probably the major issue is the service life. I mean, we can't estimate something accurately for 30 years. We just can't do it. We don't know what it's going to cost 30 years from now. And that one assumption that applies to bulldozers and Honda Pilots and maybe even real estate about the discounting probably is not helping us. It's probably not helping us. At the end of the day, we're stuck with it. Okay? So, bullet number 2 is the important takeaway here. Understand what your input values are. challenge them. Run the analysis 2 or 3 times and see if the decision changes. Missouri DOT had a very interesting result on their ADAB program. The first 290 ADAB projects, and they, by the way, have alternative pavement designs on all their projects. 4 times the life cycle cost adjustment factor changed the decision on which one was the lowest cost. You know, and being totally pragmatic, why have this controversy about life cycle cost when, if we want to award it to the lowest bidder, do 2 designs, let them compete against each other, and whichever one's low wins? To me, that's a very simple thing. But unfortunately, the emperor has no clothes. And we don't want to admit that we can't calculate ourselves down to a nearest significant figure when it comes to estimating something out 30 years from now. So the bottom line is we can help ourselves if we use simulations. That to me is probably the biggest thing. I mean, at risk or crystal ball is cheap. It works on Excel. I mean, I'm a guy that punched cards and learned Fortran 4 for my programming language. I figured out at risk without having any help other than just turning it on and using the help button when I couldn't find the right thing on the menu. It worked. It's an excellent way to do that, and I'm not pushing that. There's plenty of those. There's even freeware that's Monte Carlo simulation. So simulate it. I mean, right there, now it's easy. I don't have to defend why I picked 4%. I can say, go to that table that I showed you on interest rates and say it was somewhere between 1 and 8%. And I let it vary in accordance with the way it occurred in terms of the legislation or what was currently used across the United States, across the world. At the end of the day, I think the point I'd like to make is that what we're really looking for in this type of a situation is the least sensitive option, okay? Not necessarily the low cost option. We're looking for the one that, using life cycle cost analysis, is least affected by changing the input variables. That is the one that has the highest probability of being the lowest life cycle cost. And with that, I'll open it up to questions, spears, tomatoes, whatever you want to throw up this way. Good. I may actually get out of here alive.